we're going to learn two applications of integration, or not two applications, one application of integration, two different methods, and that's how to make volumes, okay? If we have an integral, can we make a volume out of an integral? In the previous section, or previous chapter, we saw that the integral gave us areas, but can we extend this to volumes? And the answer is yes. If you take Calc 3, you are going to be finding integration. Triple integrals are equal to the volume, or double integrals are equal to the volume of the function you are looking at. So this first method is by volumes by disks and washers. All right, so let's go ahead and read the definition of volume. It says, let S be a solid that lies between x equals a and x equals b. If the cross-sectional area of S in the plane P sub x through x perpendicular to the x-axis is a of x, where a is a continuous function, then the volume V is equal to the limit as n goes to infinity of the sum of I equals 1 to n of a x sub I star, it's a really bad star, delta x. You've seen a familiar definition before when we were talking about areas. Area was equal to the limit, blah, 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 blah. And this right here was the height of the rectangle. This was the width of the rectangle, okay? So the idea extends to volumes in such a way that if I have a solid, now, of course, look in the book for a better picture. My picture is not going to be that great. But let's say I have a solid from A to B. There is a behind here. I think it would be more like this. Say I have some solid right there, okay? What they mean is if this is my solid S from x equals A to x equals B, if I were to look at a plane, so a small little cross-sectional area on here, and I were to find the area of this very thin slice, that's what my A is. Down here is my delta x. Here would be the area. And all I do is break it up into a bunch of little areas and then add them up. Do an infinite number of areas throughout the entire piece. You're going to get the volume. Alright, so that's the idea behind making volumes. So what we want to do, I forgot to write this piece. This ends up being the integral from A to B of the area, it's a function of x, dx. Okay? Now let's find a way to make a solid. This is called solids of revolution. A solid of revolution is when you take some function from right there to right there, x equals a, x equals b, and what we're going to do is we're going to revolve this around the x-axis. So we're going to take this and revolve it around the x-axis, and if you were to draw this shape of what it looks like after the revolution, well, that part's flat. If I'm revolving it in a circle, it's going to give me a circle, something that looks like that. We've got this shape, so something that looks like that, and it's also going to be on the other side. So right here would be x equals a, and then over here would be just another circle if I wrap it around like that. So this whole piece right here is circular, so over here would be x equals b. So we're just revolving it. Now if you're looking at my lecture notes, you could see what's going to happen when we revolve it. what we're doing here, this is called the disk method, okay? If I were to have another graph, blow it up a little bit, and I was revolving this shape, and remember how we define the integral. We've defined the integral as the sum of a bunch of little rectangles. Now, if I were to take this rectangle and revolve it around the x-axis, the shape that I'm going to get is a circular disc, okay? It's going to have some width, it's going to have some radius. It's a very thin little disc. This is delta x, okay? So we're revolving every single one of these discs or every one of these rectangles in a disc. That's why they call it the disk method. You're making a bunch of little discs. They all have a corresponding area. The area of this disc is pi r squared. So you can think of a bunch of little circles. You're adding up all the areas, and you get the volume of the solid figure it makes. Okay? So let's see, pi is just the constant. What is the radius of this disk? Okay, the radius of this disk is whatever this height is right there. Well, that height right there is just whatever the function is at f of x. So the area as a function of x is equal to pi times f of x being squared. So all you do to find the area of a little disk is you take the function, you square it, and you multiply it by pi. So a solid of revolution, the volume of a solid of revolution from A to B was the integral of all the areas. Well, if our areas are all disks with the radius f of x, so this is just the area of a circle right here, pi r squared. The radius is our function. This becomes the integral. I'm going to bring the pi on the outside because pi is just a constant from A to B of f of x squared, really bad too, squared dx. So this is revolving a function about the x-axis. We're revolving it around the x-axis. Now, you can revolve around the y-axis. So, revolve around y-axis. Well, the volume is the integral from c to d, where these are y limits of integration, pi f of y squared dy. Looks a little funny because it's in terms of y. Normally we have functions in terms of x's, but sometimes they want you to revolve the function around the y-axis. And all you have to do is solve your equation for x, and it's the same formula. You just plug your function in, square it, integrate, multiply by pi. We're going to see that in examples. The first example we're going to go through, it's more of like a proof example. It's show that the volume of a sphere is 4/3 pi, oops, not r squared, r cubed. We're going to prove that right now. Okay, where did they get this formula from? There's probably geometric versions of how to get this formula. This is a calculus version of how to get this formula. What we're going to do is we're going to look at the equation y is equal to square root r squared minus x squared. If you recall what this equation is, this is the equation of a top half of a circle that goes from negative r to r. It has radius r. Now, if I want the bottom half, I'd put a negative there, because this is an implicit equation. It really is x squared plus y squared is equal to r squared. But when I solve for r, we get a plus or minus this square root. So here's what my function looks like. And what I'm going to do is I'm going to apply the disk method. I'm going to take a little disk like this. So there's my disk. And I'm going to revolve it around the x-axis. If I take this shape, it's a half circle. And if I were to revolve a half circle, it's going to make a sphere. It's going to make a sphere of radius r. Everywhere it has a distance of r from the origin. So this is going to be the integral from negative r to r. There's a pi out front, just from the disk method. And I'm going to take the function r squared minus x squared. I'm going to square it and integrate dx. Now the square root and the square cancel. And I get pi times the integral from negative r to r of r squared minus x squared dx. This is a straightforward integration. You get pi times, this is just the constant, r squared x minus, undo the power rule, 1/3 x cubed. I'm going to evaluate it from negative r to r. So I don't need anything on the board right now except for this. I'm going to erase these. Let's go ahead and evaluate it. Let's plug in r. Let's plug in negative r. So I've got pi times, I'm going to plug in r squared times r minus 1/3 r cubed minus, so this is from plugging in the upper limit. Now I'm going to plug in the lower limit. R squared times negative r. Oh, that has another parenthesis. Minus this entire thing. Minus 1/3 negative r cubed. So this is pi times, well, right here, that's r cubed. Minus 1/3 r cubed. Minus, this gives me a negative r cubed. Minus a, okay, so see, this gives me an r cubed with a negative r cubed. Negative r in parentheses cubed is negative r cubed, but since there's a negative here, it turns into a positive 1/3 r cubed. Well, then let's see what's going on in here. R cubed minus a negative plus, so r cubed plus r cubed is 2r cubed. We still got the pi out front. Minus negative, that makes that a minus. So negative 1/3 r cubed minus 1/3 r cubed is minus 2/3 r cubed. So running out of room here. So we don't need this anymore. We already plugged them in. Oh, that negative r is gone. There we go. So let's see, if I were to put these two fractions together, this is 6/3 r cubed minus 2/3 r cubed, all multiplied by pi. They're like terms. 6 minus 2 is 4/3. We've got the pi right there, r cubed. So we just shown that a sphere of radius r has a volume of 4/3 pi r cubed. So that was doing it by the disk method. And all we did was square the function and integrate it from a to b and multiply by pi. Now, there's another method. It's called the washer method. And that's to say, if you have two curves, let's say I have one curve that looks like that, and then I have another curve that looks something like that. So right here would be y1, right here would be y2. Now let's say I wanted to revolve that around the x-axis. How would I do that? So the area in this case, the area of this piece right here, if I were to make a radius, it's going to be pi times the outer radius squared minus pi times the inner radius being squared. The outer radius, so here's my x-axis, the outer radius would be y1. It's further away. It's on the outside. The inner radius is on the inside. What we mean by that is if we were to revolve it, what's going to happen is you're going to have, now it's not representative of this shape, you're going to have something that looks like this. And it's going to have a hole in the middle. And it's going to be revolved around. It's going to have a hole straight through. If any of you are taking engineering graphics, you may know what I'm talking about. Like if this was a revolution and you got an extrusion in the middle, okay, it's going to have a hole. And they call it the washer method because if you were to take, like if I were to make a small little rectangle right there, the little rectangle would be there and also right there. If I were to revolve this rectangle, it's going to create something that looks like a washer. And if you're looking at my notes, they have a much better picture of what this looks like. And if you look in the book, again, this is really hard to draw by hand. I guarantee, I would definitely look in the book just to see what I'm talking about, to get a better understanding than my drawings over here. Now, someone may ask, why don't you do the outer radius minus the inner radius and then square it? Okay, so you don't do the outer radius minus the inner radius squared because they're actually, these two things, these two expressions, if I were to write it like, here's the question. Is the outer radius squared minus the inner radius squared the same thing as the outer radius minus the inner radius squared? Are those two the same thing? Answer is no. Here, if I were to multiply this out, you get the outer radius squared minus the outer radius times the inner radius plus the inner radius squared. If you look at this side, you get the outer radius squared minus the inner radius squared. I'm leaving the pi out, okay? We don't care about the pi. They both have pi on each side. If you look, these two expressions are not the same thing. When you're doing it like this, you are not computing the solid of revolution that you want, okay? You are doing a solid of revolution, but it's going to be a different solid. It's going to be the solid when you take the outer radius minus the inner radius squared. Okay, outer minus inner, then squared. This one, what this one is doing is, imagine, I'm just going to draw a cylinder just because those are easiest to draw. If I were to take, this is my outer radius minus my inner radius, this one generates the solid of revolution on the outside. This one generates the solid of revolution on the inside, and you subtract them. So if I were to do something like this, what it's going to do, if this is my outer radius, it's going to create that. My inner radius, it's going to create that. It's going to subtract the volumes from each other. It's going to do the big volume minus the little volume. Subtracting these two functions here does not necessarily give you this shape. It actually gives you a different shape than what we have, what we actually want right here. So that's the washer method. Let's go ahead and do some examples to illustrate the disk and washer method. What you're going to want to do is you're going to want to graph these. So you can see what you're revolving. You need to know what the outer radius, inner radius, and stuff like that is. But y is equal to x plus 1. Y is equal to 0. X is equal to 0. and x equal to 2. And we're revolving about the x-axis. Now this is important whether you're revolving around the x-axis or around the y-axis. Since we're revolving around the x-axis, it's going to be the integral from, they told us our limits of integration from 0 to 2, with the pi out here, x plus 1 squared dx. Our function being squared dx. Let's draw a picture of what this looks like. X plus 1, start on the y-axis at 1, 1 to 2. We're going from 0 to 2. And then, let's see, up 1, 3. The graph looks something like that. And we are taking this little shape right here, this trapezoid, and we're revolving it around the x-axis. If I were to take a little disc like this, that's my little disc. If I were to revolve this, I'm going to get something with a smaller circle on the inside. It's going to look something like that. Okay, this should be dotted. Something like that. It's like a cone without the tip on, without the pointed tip. That's what we're drawing. I believe it has a name. I think it's called like a frustrum or something like that. But that's the solid of revolution that we are drawing. So, here's our radius. All we have to do is take our radius, square it, integrate from 0 to 2, and multiply it by pi. So, there are a couple ways you could do this. You could do u substitution on this one, or you can multiply it out. Let's go ahead and multiply it out. 0 to pi, or sorry, not 0 to pi, 0 to 2, pi out front. This is x squared plus 2x plus 1 dx. Integrating is just undoing the power rule. 1/3 x cubed plus x squared plus x evaluated from 0 to 2, and I'm going to multiply it by pi. Now what's really nice about this problem is that we've got the 2 right there, or sorry, the 0 right there. This is a polynomial, so plugging 0 into there is going to not do anything for us. All we have to do is plug in 2. So this is pi times 1/3 times 2 cubed plus 2 squared plus 2. Let's see. I get 26 over 3 with a pi. Bunch of fractions. You can go ahead and plug it in your calculator. Just be careful plugging it in your calculator. 26 over 3 pi, and that's the exact area of this thing. Let's go ahead and do another example. Let's see, it says y is equal to 2x, y is equal to x squared, and then we're revolving about the x-axis. Again, let's go ahead and draw this. So at 1, 2, 1, 2, 3, 4. This one at 2, we're at 4. And this one at 2, we're also at 4. It looks something like that. So you could see we're integrating from x equals 0 to x equals 2. Now, they just so happens they cross nicely. If they did not cross nicely, you take the two equations, set them equal to each other, and you could solve for those intersection points like we did in 6.1. So, here, we're going to have to use the washer method. Now, a little disc is going to look something like that. Alright? And when we revolve this, this is going to look really weird. So when we revolve this, on the outside, it's going to be straight, and we're going to have a little circle here. And then on the inside, see, it's going to look something like that, where, oh, that'd be solid. Where in here is all solid and inside here is all hollow. Oh, that comes down to a point, not a circle. Comes down to a point. Like that. Again, the drawings of these are really bad. Probably want a computer to do the drawings. So, this is going to be a washer method. I've got an upper function, I've got an upper radius, and I've got an inner radius. I said upper, I meant outer. So, this is the outer radius, this is the inner radius. So, when you're doing a washer method, it's the integral from a to b, you've got the pi out front, of the outer radius squared minus the inner radius squared dx. So this is going to be the integral from 0 to 2 of the outer radius, 2x squared minus the inner radius, which is x squared squared. We got the dx. Now that we have our integral set up, we don't need any of this. See, we actually don't need this. Integral from 0 to 2. This is going to give me a 4x squared minus x to the 4th dx. All I do is square everything. Now we can undo the power rule. I forgot my pi out front. Pi times 4/3 x cubed minus 1/5 x to the 5th, evaluated from 0 to 2. Once again, we have a zero limit of integration, a polynomial, so when we plug 0 into there, nothing's going to happen. All we got to do is plug in 2. Pi 4/3 times 2 cubed minus 1/5 times 2 to the 5th. Now I just plugged this piece right into my calculator and turn it back into a fraction. And if you do that, 64 over 15 pi. The pi is coming from here. All I did was plug this entire thing on my calculator and turn it into a fraction. You get 64 over 15 pi. Alright, so next example says x equals 1 plus y squared. It says y is equal to x minus 3, and they want you to revolve it about the x-axis. So that's this axis right here. We're revolving around this way, around the x-axis. If you recall, that's the integral from c to d of f of y being squared dy. Now, this is going to be a washer method because we have an upper curve and an outer curve and an inner curve for our radii. So this is just the general. If there's only one function, you take it and you square it. Okay. So let's go ahead and draw our functions and see where our outer and inner curves are. So let's see, about the x equals 1 plus y squared. That's going to look something like this. Y equals x minus 3. Now, this is a little easier to draw. 1, 2, 3. Let's see. 1, 2, 3. It looks something like that. And we're taking this area, we're making our discs this way, and we're revolving it around the x-axis. So if I were to draw what this may look like, let's see. Circle, and then it's going to be something like something similar to what we had a bit ago. Okay. Now, if you look at this, for revolving it around the x-axis, this is my outer function, this is my inner function. So, right here, this is my inner function. This one, I'm going to solve for x. I get x is equal to y plus 3. This right here is my outer function. Now, what I need to do is I need to find my limits of integration. From where to where am I integrating from? You just set the two equations equal to each other. 1 plus y squared is equal to y plus 3. If I were to solve for or get everything equal to 0, y squared minus y, let's see, minus the y minus the 3 over, you get minus 2 equals 0. Factoring, you get y minus 2, y plus 1 equals 0. So y is equal to 2 and y is equal to negative 1. So that means right here is negative 2 and up here is positive 1. I said that wrong. You get negative 1. This is negative 1. This is positive 2. There we go. I knew something was up. So we're integrating from negative 1 to 2. Of course, my picture doesn't match it, but then again, it's poorly drawn. Go off what the math says. Oh, I should have left my equations up there. So let's see, x is equal to y squared, 1 plus y squared, and then x is equal to y plus 3. This was the outer, this was the inner function, if you recall. So we're going to integrate this from, we said negative 1 to 2. There's a pi out front. I'm going to take my outside function, y plus 3, I'm going to square it, minus my inside function, I'm going to square it, dy. So the next step, negative 1 to 2 pi, would be multiply every, oh, this has a squared here, it's squared, squared. Square this piece, put together like terms. I did that really quickly. Let's see. It's negative y to the 4th minus y squared plus 6y plus 8 dy. So, pi times negative 1/5 y to the 5th minus 1/3 y cubed plus 3y squared plus 8y evaluated from negative 1 to 2. Now, plugging all of that in, I would use the calculator to plug it in. You plug in 2 minus, you plug in negative 1. Make sure you use parentheses, but you get 117 over 5 pi. We have one more example to go through. And that is, what if you wanted to revolve one of these disks about a different line? And that's what this next example is. It's y is equal to x squared plus 1, and y is equal to 9 minus x squared. And you're revolving about the line y is equal to negative 1. What this is going to look like, this is just a really rough sketch. You're taking one of these disks and revolving it around this line. Now, you have to be a little careful. It's not the standard outer curve minus the lower curve. This one would be the outer curve. This one would be the inner curve. All of the other examples, we were always revolving around the x-axis or the y-axis, but not around a line, a different line. When doing the disk method, to get your radius, so this is the outer radius. When you find your inner and outer radius, when you're revolving about a different line, you look at the line, this is the outer line, so this 9 minus x squared, and you do the upper curve minus the lower curve. The lower curve in this case is y equals negative 1. So the upper curve is 9 minus x squared, so this is the upper curve. Just like in 6.1, we did upper minus lower. Minus negative 1. This is the lower curve. And you're going to get 10 minus x squared. So that's our outer radius. And then the inner is the upper curve minus the lower curve. So this is the upper curve for the inner part of the radius. It's this x squared plus 1 minus the lower curve, negative 1. Now, don't always think they're the same. It depends where the curves are positioned. Look for the upper minus lower radius. So this ends up being x squared plus 2. Negative, negative turns into a positive. Now we could rewrite our integral for this problem. I actually forgot to find the limits of integration. So if I were to look at this, one of them goes like this, the other one goes something like this. We're looking for that limit of integration and that limit of integration. I believe it's 1 and negative 1. No, it's negative 2 and 2. So how to get that, you set the two equations equal to one another. X squared plus 1 is equal to 9 minus x squared. You get 2x squared is equal to 8 by adding the x squared over, minusing the 1 over. Divide by 2, you get x squared is equal to 4. X is equal to plus or minus 2. It's very important. We need those limits of integration. So this becomes the integral from negative 2 to 2 of the outer radius. Oh, pi out front. The outer radius squared minus the inner radius squared dx. Now we just gotta foil this out, and then integrate. So, I already did that. Have it on the paper. You get negative 24x squared plus 96 dx. That's if you were to square this piece, subtract them, you should get this expression here. Now, if you were to integrate this, let's see, you get negative 8x cubed plus 96x evaluated. I'm forgetting my pi out here. Evaluated from negative 2 to 2. So if you were to go ahead and do that, plug in -2, you're going to get 256, and then we've got the pi over there. So this is it for the disk and washer method. The next section will cover the shell method. It gives us a better way of revolving something about the x-axis. Let me show you what I mean. Let's say I had an equation that looked like this. Y is equal to negative x to the fourth minus 3x cubed plus 1. And whatever this graph is, I could tell you that it may look something like a negative, something like that. I don't know. I just made that up. It's a negative fourth power, so it goes down. It may have some bumps. And let's say we're going from 0 to B, or sorry, A to B, which is going to be 0. And we want to revolve it around the x-axis. So that means we need to actually go from, this would be C, from 0 to whatever D is. Now to do that, that's the integral from C to D pi f of y squared dy. So what we would have to do is we would have to solve for x in this equation. That may be very difficult. I don't think we could solve for x in this equation no matter how hard we tried. So the shell method allows us to make this revolution around the x-axis without any trouble at all.